Hello mathematicians, let's take a look at the second part of this very short topic, which is logarithms. Logarithms sound technical, but they're not really. So the word description is that the log base a of a positive number y is the index when the number is written as base a raised to a power. How's that for a mouthful? It looks a lot more succinct when you write it mathematically. So if y equals a to the x, then x is equal to log base a of y. Now essentially it means that if we have y equals a to the x, then what we're doing is that the log of y is the power that you would need to raise a to become y. So a to the x becomes y. Now, I find it even easier if we remember one simple relationship and then we've got the pattern worked out. So we know that, for example, that 100 is 10 squared. Now, if I take log of 100, then I'm saying 10 raised to the power of 2 equals 100. So it's like this sort of revolving relationship. So if I take this bit here, for example, and I take the log of 100, then this 10 floats down here, so it sort of goes over around into here, and I'm left with the 2. So this is the relationship, that the log to base 10 of 100 equals 2. Now your calculator can calculate these things. We'll have a look at that in a moment, but we can work lots of them out without or just using the definition, and remembering that the calculator is limited to logs of base 10, or as we'll see later on, logs of base e, which we'll encounter later in the course. So let's look at these examples then. So a lot of it is how we read it. So again, based on this information up here, our connection is that 3 raised to the x is equal to 9. So this is the alternate notation, if you like. If x equals log base 3 of 9, that means that 9 equals 3 to the x. And then it's an index equation to solve, which is just 2. So notice here we've formed an index equation which we've solved. Later on in the course we'll see that the use of logs lets us solve index equations as well, because it's two forms of the one problem. This next one, 4 raised to what power gives me 64? So it's really saying this. We don't have to write this, but it's saying this. So of course 4 raised to the 4th power gives me 64. 7 raised to what power gives me 1 on 7? Well, that is minus 1. And 4 raised to what power gives me 1 on 64? Well, it's raised to the 4th power, and to get the negative, to get the 1 on, we need our negative. This next line, 7 squared equals x. So that's how we rewrite it. This to that power gives us this. So of course x is going to be 49. Once we've got that relationship, then away we go. So x is 4 cubed, which is going to be 64. So that means my answer up here was wrong. That's just 3. 13 to the minus 1 equals x, so x is 1 on 13, and x is 5 to the minus 3, so that's 1 on 5 cubed, which is 1 on 125. Okay, for our last variation, x raised to that power equals 49, so the base is obviously going to be 7. Now, somewhere in that definition it said that base had to be a positive number, so that's why we're not saying plus or minus 7. In this one here, x squared equals 10,000, so x is going to equal 100. So again, that to that power equals that. X to the 1 equals 11, so x is equal to 11. And on this one, x to the minus 2 equals 1/9, so x must be 3. On our next examples here, says to rewrite it in index form and then solve it for x. So a to the x equals a, obviously x equals 1 then. A to the x equals 1 on a, so x equals minus 1. And a to the x equals 1, x equals 0. Now there are some log laws which, as you would expect, are related to the index laws that we looked at previously. So the first one is the product law or product rule, that if we have the log of a product, it equals the sum of the logs. The quotient rule, if we have the quotient, or the log of a quotient, then that's the log of x minus log y, log of the numerator minus the log of the denominator. And if we have log of x raised to the n, that is n times log x. Notice here that this n is just applying to the x. It's not that thing, which is entirely different. So, down below, how do we use these in examples? I'll just do a selection of these, probably the bottom row here. So if we have log base 15 of 3 plus log base 15 of 5, then by this rule up here, that means that that's equal to log base 15 of 15. Can I simplify that? Yes, because 15 raised to what power gives me 15? Well, it's 15 raised to the 1. So the answer to B is simply 1. For our D here, log base 12 of 72 plus log base 12 of 2, then that's log base 12 of 72 times 2, which is 144. And of course 12 squared equals 144. And for F, log base 6 of 18 plus log base 6 of 2 is log base 6 of 2 times 18, which again is 2. Down below, same sort of thing. Log base 4 of 20 minus log base 4 of 5 is log base 4 of 20 divided by 5, which is of course 4. And 4 raised to the 1 gives us 4. This one here, log base 5 of 50 divided by 2 is this, which is then equivalent to 2. And log base 2 of 96 divided by 3 is going to be log base 2 of 32, which is 5. Now, with our power rule, then if we have log base A of 16, for example, and I'm trying to simplify that, again, this is the case of knowing the powers makes life easier, and your calculator doesn't help a lot except for double checking. So we recognize 16, for example, as 2 to the 4th. So that gives us that this is 4 log base A of 2. We can't go any simpler because we don't know what A is in this case. For log base A of a half, then if we recognize that that's log base A of 2 to the minus 1, then that gives us minus log base A of 2. Log base A of 1 on 32 is log base A of 2 to the minus 5, so that's minus 5 log base A of 2. And log base A of 1 on root 2 is log base A of 2 raised to the half for the square root and minus a half because it's got 1 over it. So that's equal to minus a half log base A of 2. These ones down here, given that log base 2 of 3 equals that, because at the moment we can't use the calculator to get that, and log base 2 of 5 equals that, use the log laws to find these things. So if we have log base 2 of 15, then I've got to recognize that 15 is going to be 3 times 5. So that's log base 2 of 3 plus log base 2 of 5, which is just equal to 1.58 plus 2.32. I won't work that out. Our next one, log base 2 of 10, then at first glance it looks like we haven't got enough information because we've got 5s and 3s, and we know that 10 is 2 5s, and that we could write that But log base 2 of 2 is just 1. So we've got 1 plus log base 2 of 5, 1 plus 2.32. Log base 2 of 3 on 2, same thing. We've got log base 2 of 3 minus log base 2 of 2, and we know that log base 2 of 2 is 1. And lastly, log base 2 of 2 on 3 is log base 2 of 2 minus log base 2 of 3, and once again that's equal to 1. Now you may have already picked up that there are some common log relationships or identities which are so frequently used that it's worth knowing them. So we use the one up above. If we have log, no, I don't think we actually did use this one. Log base a of 1 is 0 because a to the 0 is 1. So log base anything of 1 is equal to 0. We did use this one where we talked about log base 2 of 2 equaling 1. So log base a of a equals 1. So because a to the 1 equals a. Likewise, log base a of 1 on a is minus 1. Log base a of the square root of a is always a half. Log base a of 1 on x is equal to log base a of x to the minus 1. And by the power rule, that minus comes down the front. So it's equal to minus log base a of x. You might need to read those and reconvince yourself of those, but you're going to use them so often that hopefully they'll become reasonably comfortable for you. Now the last point before we leave logs, we come back to them often in the course, is to realize that the log function and the exponential function are mutually inverse operations. Now you might remember we've come across inverse operations before, and we said that they cancel each other out. They're formed when we essentially swap the place of y and x, and they also have a graphic relationship as well, and that is that they are reflections of each other in the line y equals x. So if this was the curve y equals a to the x, and it would cut through at 1, this would be the curve y equals log base a of x. So they're reflections in that line. Again, much more on that later on. So if we take the log to base a of a to the x, then the answer is x, because obviously a raised to the x gives us a to the x. What's maybe not quite so obvious is that if we take a raised to the log base a of x, that takes us back to x, because the exponent and the log are opposite operations. So it's like taking the square of the square root. We just get back to what it is that we're operating on. So if we take, for example, log base 7 of 7 to the 12, these two operations cancel each other, and our answer is just 12. And if we take 5 to the log 5 of 11, those two operations cancel each other, and we're left with 11. Now part B says write 3 as a power of 10. So that would be 10 raised to some power equals 3. We don't know that power, but we could solve this equation, because if we took the log to base 10 of both sides, so if I took log base 10 of 10 to the x equals log base 10 of 3, then log base 10 of 10 to the x just gives me x. So x equals log base 10 of 3. So I'm saying 10 raised to what power gives me 3. So while I couldn't solve this index relationship up here, because I don't know what power you raise 10 to give me 3, if I use my log relationship and operate on both sides with log, because it's an equation, then the log and the exponential operation cancel out here. So now I can solve that equation. I can go to my calculator and I can work out log base 10 of 3. So I'll just get the calculator up, and I can see on my calculator here that on this key I've got 10 to the x and log, so that means that this is the log base 10 key. So if I take log base 10 oops, it is, I've pressed it twice. If I take log base 10 of 3, where's the close bracket, then that will give me 0.477. And if I think about whether that makes sense or not, then 0.477 is about 0.5, and 0.5 is a half, so 10 raised to the half, square root of 10, is that around about 3? And of course it is. So it does actually make sense, so I can work back and get my answer. 0.477, I think that said. Now, 7 as a power of 2, then it's saying 2 raised to what power gives me 7. And I could again operate log of both sides, so log, but I need log base 2. So log base 2 of 2 to the x, so that these cancel out to give me x, equals log base 2 of 7. So x equals log base 2 of 7. Now unfortunately my calculator doesn't have a log base 2 button. It's only got log base 10 and log base e. So I have to use something called change of base. Now change of base doesn't make it this far into the chapter. It is on your reference sheet and you will use it later on, so I'll just mention it now. And it allows us to use the calculator to work out something like log base 2 of 7. And it says log base A of B is equal to log base something of B and log base something, or divided by log base something of A. And if we pick this something to be something our calculator can help us with, then we're set. So this could be log base 10, or it could be log base E. Now because we only know about log base 10 at the moment, that's what we'll operate on. So we can come back to this one here, and we can use change of base to rewrite this as log base 10 of 7 over log base 10 of 2, and we can work both of those out on the calculator. Well, let's just check how we do the calculation on this. So I can either literally put in log base 10 of 7 divided by log base 10 of 2, or with this calculator most of us have got, I can use that fraction key, and that will give me log base 10 of 7 divided by log base 10 of 2 equals 2.807. So my 2.807, I maybe should check to see whether it's reasonable. So so this is close enough to 3. 2 to a little bit under 3 gives me something a little bit under 8. It's all good. Again, might be a good time to put together a few points for your summary and start the exercises.